Hey everyone, Patrick, the Everyday Machinist. In today's video, it's going to be about micro fixturing. So I kind of ran into an issue with making 262 of these stainless steel standoffs. It's an 832 thread all the way through. They're 3/8 of an inch by 3/8 of an inch, and they're 590 thou tall. I approached it in a couple different ways. One of them not really working, just because of limitations with the machine we have, and that would have been running round stock, probably 5/8 round stock. Could probably get 1/2 inch out of that. No, definitely not. 5/8 round stock, and have it in a CNC lathe, but would require live tooling, which I don't have. So that kind of would have been ideal, I think. Does poses its challenges for that, but we can catch parts on that machine. But again, that's off the table because we don't have live tooling. The other way I thought about it too is, again, purchasing 1/2 inch material, or now purchasing 1/2 inch material, square stock, so 1/2 inch square stock, and kind of cutting it down and kind of making multiple fixtures to do that. I think like a rigidity standpoint would have been an issue. You could have done it. I just think it would have been, I want to fixture this and walk away. And that's ultimately what I came to with the final idea with making these. Is just I purchased a piece of 2-inch wide flat stock stainless steel 3/16, and I think it was 5/8 of an inch thick, so we had just enough. Yes, I could have ran thicker, but the next size would have been what, 3/4. So that's more of an 1/8 of an inch I have to try to take off of that raw stock, and I could have done it, 60 thou on the top, but again, I want material underneath it to be able to hold it and be able to cut all the way down. So if you think about that, me flipping the part and then trying to hold the part, which I achieved, but now I'm trying to take off over an 1/8 of an inch, or close to an 1/8 of an inch. So I thought that was kind of silly because it's just that much of a part. We don't have much here. So you can see this is a strip of, I think there's 7 here. And what I wound up doing is laying them out in 4 rows wide by 65 long, somewhere around there. We made extras. And leaving 145 thou gap in between each one. We ran an 1/8 inch 5 Flute end mill. This is actually from Accupro. I'll pop a picture up here of this stuff. This is from Accupro, 1/8 inch 5 Flute, 10 thou radius, corner radius, and it actually worked out really well. It's only a 1/2 inch length to cut. We were able to get down some because we kind of roughed it down. We're doing 2 operations after we're done with the first part, and that is putting them inside of this little fixture here, which I'll give you a little close-up of it. But basically, it's a machined part here, okay, and it's sitting in the hard jaws. We machined a 3/8 wide, a little over 3/8 wide channel going down the middle of that. So we're getting a lot of bite on the material, keep it from going side to side. We are facing it this way, facing the raw stock off, and then just finishing the profiles from what we can grab. It's about 100 thou down on the program, and just to clean it up, and it's been coming out fantastic. So I'm not going to change any of that. And surface finish wise, it's coming out really well. Not the greatest, but we have to passivate them, and we have to, well, first we're going to be vibratorily tumbling them with a kind of medium grade media. So we have to do that first, and then we're going to passivate them. If you don't know what passivate is, look it up. It's just kind of prepping the surface for biologics. From my experience of doing it with biochemical companies, what they do all the time is you can use nitric acid, you can use citric acid powder formed in a solution, so concentrate, same with nitric acid. Nitric acid is very expensive. I will be using a citric acid base concentrate with a certain amount of water to get a dilution percentage. And basically it just kind of prevents the transfer of contaminants or the ability of contaminants and oxides to kind of stay stuck onto the metal, to be transferred. Again, these are electronic standoffs. That's about as much as I'm told they are. So I do have hard jaws in here, so this is actually sitting in the hard jaw. I have it modeled pretty well. As I run a few strips of these, this is 11 actually, when we were cutting them out of the overall flat bar, they were still all connected. A little bit of, I just wound up cutting stuff to make it easier to get it through the bandsaw, and they weren't all 11s, so some are 7s. But when I actually face down my hard jaws, I rarely use them, so I just skim them. Okay, usually they're sitting in the tool room, and I'm never using them. I skim them down so they're nice and even. And for the first operation, I wound up putting a step like you see here, okay, in the raw stock on both sides, like you see here, in the 2-inch wide raw stock, about 30 thou by 30 thou deep. Put it into all 5 vices here in the VF5 and ran the program. And it honestly wasn't that long. It definitely was hours, but it went a lot faster than I anticipated. Now, I'm running a 25 thou axial, so depth of cut. We're slotting, and I think I wound up, I went through one tooling to learn, figured it out, and the next tooling I broke, that same tool where I kind of figured it out on, I forgot to make the change of me kind of walking in the surface foot. So I don't really care if it's $14. I do care, but I anticipated breaking tools on this. So with that, so I was able to get it in at, I think it's 4,890 RPM, and the surface speed is 14 inches a minute. So it works out to 7 tenths and some change on per tooth. So that worked really well with the full slotting and everything. Now we're only able to go down a little bit. Now with tapping, so I left them all in there with tapping. I left everything in there, we drilled. After drilling, so with the program versus, program versus reality with drilling, it actually, I don't think I have some here, but I thought we'd probably make it out. But you can see here, that's, the drill went all the way through, but at the first time I did it, I programmed it for the drill to come down, but it didn't come down far enough. It's stainless, a little harder, trying to push it out of the way. It didn't happen. I'm running a 2-flute stainless steel tap. I get them from McMaster, 832 tap. They're like a black oxide finish. Try to get this into the camera so you can see that, hopefully. Okay, and then there is the, hopefully you can see that. But again, I'll put pictures in if it doesn't come out too well. The 5-flute 1/8 inch. So originally I ran one tap, and I'm machine tapping. One thing I learned on that, we'll start off with the first thing I learned. Since the drill wasn't going all the way through, breaking out the bottom of the hole. Now again, I already accounted for extra stock, for the remainder stock that was on this part here, about 90 thou, actually a little over. Well, what happened was, as the tap is coming through the hole, it can't push the chips out the bottom. So therefore, I think I only got through 10 holes before it broke the tap. So kind of revisiting that, I realized what the circumstance was on that. So I wound up coming back in, drilling all the holes a little deeper, which I just started from the depth, or a little bit higher than the depth they were currently at for time, carbide drill, and went through and just kind of reopened the holes, and then put my other tap in, and it ran through no problem, and it's still in the machine. So that's definitely something to consider. Now, I only ran 100 RPM, which seemed pretty good. So I ran 100 RPM, and that also with Fusion kind of auto calculates your surface feed and how fast it's coming, just because of the thread pitch and size. So 100 RPM on that. I think that took about 30 minutes, 32 minutes to do that, but better than me trying to do it. So that worked out really well with that. So keep that in mind. Hopefully, if this information does help you, definitely drop a comment down below. Any questions, drop a comment down below. I usually respond to most of them as long as they're reasonable. It helps me grow the channel, helps the algorithm, all that fun, happy stuff. So I really appreciate it. Again, I do respond to these comments, good or bad or indifferent, as long as it's on topic. I really don't care. I'm not perfect. I think the name of the channel, The Everyday Machinist, I'm not like the expert everyday machinist or whatever. It's just my opinion, my take on it. And I love the feedback. Like I said, good, bad, or indifferent. Everybody has their way of doing it. So everybody gets to learn. It's really the whole goal of the channel, right? So I'm learning, you're learning. We can all be friends. And at the end of the day, it's just YouTube. So hopefully that helps. And again, with this fixture, I wanted to touch on too, as it's sitting there, now it's machined pretty well. As it sits in there, in the program, right, in the CAD program, what I'm doing is this is sitting in the 3D space inside of a modeled Curt 6-inch vise. And this surface here, which is machined, the surface is not, it's green from the raw stock that it was, which I purposely left it that way so I don't confuse it. Not that I could, but you could. On this side is perfectly flush with the x-axis. Okay, and obviously it's been calculated for y. If there's any difference in machine to reality, I pre-checked that. And plus, this profile was cut first, sits into the hard jaws, and then this channel is cut. And again, it's a little over 3/8 of an inch. Kind of worked with that number, and I'm down, I think it's another 3/8 of an inch. So just to kind of really keep it locked in there. Now, since they're cut with a finished gap of 145 thou in between each one, I put holes in there, okay, that correspond to it. In this fixture, there's 11 holes with an 832 slotted screw, machine screw. So I then install them. Tedious, but it's actually not terrible. They go in and come out really easily. I think it's a 4-minute runtime. So with this being at X0 in the model, okay, so the work corner offset in the program, CAM, this is 0. And then the first part is a certain amount in from 0. So when I put it into the vise, I really don't care where X is when I set it, okay? I get it pretty close. What I wind up doing is, now this machine has probing. I don't use it. It's a lot faster for me to come in here, throw the Heimer in, and which I'll show you, and indicate X. So what I'm doing is I'm clamping it in there, and every time I'm indicating this as X0. So wherever it is, that's X0. Y is always going to be the constant because it's the way it's designed and the way it sits into the vise. I do periodically check Y on both the fixture and the part as they go through, and on Z, because it is facing this off. So with that, I think I'm barely a thou, maybe a thou and 2 ticks, maybe. Big or small, mostly they've been running just a little bit under 590 thou. But yeah, so I'm using a Heimer 3D tester indicator here, okay, and this was an old ISO CAT or ISO CAT 40 taper or 40 taper ISO holder, and it worked. It fit into the dogs of the spindle, but I just wound up machining off them because they're real narrow. They're not double rowed like you normally see on a CAT 40 fixture like that. It just kind of had one fat single row, and it, you kind of manually thread it in or whatever. It didn't normally come with a pull stud, so I just kind of modified this. This way, you could just pull it right into the pull stud of the spindle, and use it. Not really have to worry about it rotating into the drive dogs on the spindle. So, but yeah, every single time we come in and we indicate our X, and then we come to our Haas control here, and we change X, whatever that value is, that is now X0. So again, we have it modeled that way with the work coordinate offset at 0. Normally, all my work coordinate offsets, because I'm modeling my table, my vise, and everything else, everything is in the CAD space and CAM space. Right back here, the back left corner. is our X and Y zero, and 1 inch above the surface of that vise is approximately Z0. So if we just stick to that general idea, then it becomes a muscle memory thing. It's consistency that kind of helps everything fall into place when it comes to multiple jobs you're running on this on a machine. So that's that. Hopefully you understand what I was explaining. It is simple, micro fixturing. Again, it's just really simple. So keeping it all together. Now we're not, again, 4-minute runtime, give or take. Just to be able to just finish these 11, we take them off and do them again, get them in a batch ready to go. I think we're doing 260 of them, maybe a little more, just so we have enough. And it's, again, I try to think, not overthink the time it's going to take to make the parts. If I have these 3 options, okay, try to give myself 3 options, and I can start checking a couple off the list, you know, logically. I'm not going to sit here for a day and try to think about, oh, maybe I could do this, or some crazy idea. It's a job shop. I'm not, I want repeatability and reliability, and it's got to be quick, right? I'm never going to make this part again, and if I do, I would do the exact same thing because I know it works. So this was a no shit, like 2-minute idea to come up with something like this to hold these parts and make it consistent. So again, I don't have time to do this. I'm not going to go out there and try to design some crazy mighty bite clamping system. The ideal situation would be on a live tooling lathe, I think. You could have had some spring back, a little bit of spring back, but you can account for that. But I think, in my opinion, is the next best thing is for the mill and to do it the way I've done it. Lay them all out on one piece, machine them. Now they don't have to be that tight. You could have ran a 1/4 inch or a 3/16 diameter end mill. My experience is we're slotting pretty far down, 550 thou, at 25 thou intervals. And in doing so, you have to run all the flute. You can't run a 1/4 radius corner chamfering, or a reduced shank. You have to run a 1/4 radius corner chamfering end mill. If not, it's just going to get destroyed pretty fast. But if you're running a reduced shank, even if, so that reduced shank, or even if you have the clearance, but it's still pretty tight in there, you have a standard straight shank with the obviously same diameter with the cutting flutes and the shank. What's happening is it's not able to evacuate the chip out because the spiral flute is not there to help it do that. Now I have air that I'll blow onto these because that was pretty critical to do that as well. But I've also tried it both ways where I'm trying to slot something that's just as narrow or close to as the diameter of the tool I'm using for efficiency. And the reduced shank, even though it's reduced shank, it's still not enough. Even though we're making micro chips, very small chips, it's still not enough, and it kind of slurries around the shank, and it's just too much for that tool, and they just snap right off at the end of the collet. And right at the end of the collet holder, they snap right off. So from my experience, I like to prefer to run a good 5 flute, stronger core to the tool, and definitely as minimal I can, but enough for the depth of cut I'm doing, of length of cut. So hopefully that might help somebody. Again, just my experience, my opinion, what I prefer to do. Yes, there probably are many other variations of tooling out there. I'm sticking with this one, but I'm definitely happy to hear your input on this and what you guys think. Quick, talkative kind of video, but down and dirty, but educational, hopefully. Please like, comment, share this video. If you're new to the channel, please consider subscribing. I'm definitely trying to make a little bit more content out there, and just as much as I possibly can with my inputs and insights without exposing too much of what I can't show you here. So thanks again. Hopefully, I'm going to try to stay consistent on a weekly video again, which should be doable. Thanks, everybody.